morning, everyone. My name is Zhening. I'm currently a PhD student at the University of Cambridge. Today I'm going to talk about a work that we conducted last year. It's named Open 3D. This is a very early work on the domain of 3D open vocabulary instance segmentations. This is a joint work with me and some of fantastic collaborators in Hong Kong and my professor, Professor John Lazenby. Right, let's talk about the background. The computer perception system is now going through a transition from the previous closed set understanding to the open world understandings. Closed set understanding refers to the system that can only understand those classes predefined in the training process. So this has a quite limited capacity in this dynamic world. While on the other hand, open world understandings, the system can understand those unseen and those diverse and even free-flowing languages and to carry out some perception tasks. This is actually more similar to how human is interacting with the world. In the domain of 2D open world understanding, it actually has developed very fast thanks to the availability of large-scale internet text-to-image pairs and also some pioneer work. Right, so at the moment there's quite a lot of work has impressive results. So what I'm showing here is actually some work from last year. I'm sure there's much more new work coming out this year. Essentially, what they can do is given a list of phrases, it could be anything, it naturally describes an object. Grounded Dino can do object detections very well to refer to those given texts, and Odyssey can do panoptic segmentations quite well. And there's another model called Lisa, which they introduced a new task called reasoning segmentations. Basically, what they do is you give a very complex sentence, which probably requires some word knowledge or reasoning to understand, and they can understand that and also give you a segmentation result. Like for example, two images here, you ask who was the president of the US, they will give you Obama and Trump's. Right, but this is not the case for 3D. In 3D, so the progress of 3D open world understanding is quite slow, mostly because there are lack of large-scale 3D text pairs data sets. It's harder to collect it because for image you can just grab from web and there will be millions of images. But for 3D, it is not the case, although I know there are some works going on trying to build such data sets. And also, the other reason is there's a huge domain gaps between different 3D data sets. Like for example, data set captured from LiDAR sensors or photogrammetries or RGBD images, they actually look quite different. And also those from simulations. So to achieve this type of impressive open world understandings, most of the approach of using images to bridge the gaps, either distill features or constructing 3D text pairs. We'll dive into the previous approach in next slides. Right, so I kind of categorize them into three groups. So the first group called feature distillations. The way they do 3D open world is that they have a 2D backbone to extract features for each images, and they have a 3D backbone to learn the features for each point. And because 2D images, we already have well-trained models, so for each, for the features of images, it's actually aligned with the languages, and you distill this into your 3D backbones. So in that case, so we're kind of hoping the 3D backbone will learn some language-aligned features. And a typical one including the open scene and click to scenes. And the other set of work, which is we call PLA families, including the PLA, regional PLC, and Lois 3D. They have a quite similar approach, but instead of using the 2D backbone to learn those features, they have image captioning models. So for each images, you use the image caption models. You will produce a text description for that images. And image can also project it to 3D to get a point cloud, and then you will build a small scale 3D and caption pairs, and then use that to train your models. And then, so hopefully the 3D models will have some language awareness. The other set of work, which is including some of the concurrent work, OpenMask 3D, the way they do it is also quite easy to understand. Like, give a 3D point cloud. The first thing they do is they propose some interesting object. It could be a bounding box or instance masks. And because you also know where those bounding boxes are in 2D images. For example, here, if you want to understand those TV, you probably will you probably can find the location of TV on those images. And you just crop out those small patches, and now you have a list of patches. You just fit them into a clip models, and clip can tell you where they are, and you just like just ensemble all the results you get from multi-view images, and you just project them back to 3D. So in that case, you can understand so each instance and their classes. Well, many of this work has achieved quite impressive results, but a limitation of this is that in order to use this work, you not only need to have your 3D point cloud, but you also need to have a well-aligned 2D images. So, but that means you need to have images, your depth map, your camera pose, and camera intrinsics. Like without any of them, this won't work. So, in this work, we're trying to solve a problem. Like, if you only have 3D point cloud, can you still do something similar without relying on those images? And this is why we propose OpenInstance 3D. OpenInstance 3D motivations is actually propose a 2D input-free framework to understand open vocabulary things at the instance level. I'm just talking a little bit quickly about why we want to achieve this 2D input-free systems. First of all, for many of the scenarios, actually, you probably won't have all those prerequisites in your system. For example, LiDAR point cloud, they often exist without 2D images, because sometimes the image used for colorization and they will delete them afterward. And for the grammetry point cloud, sometimes the depth map is not there. And then for point cloud generated from, if your 3D asset is generated from registration of different scans or converted from simulations, the 2D images is also not there. And we put some of the example open source dataset out there that is actually fit in those conditions. And also, in applications, it could happen that you probably lost your files for intrinsic or pose or depth informations, which make all the previous model not really applicable. Or you would just want to save storage, like so you remove all the images. Like for example, for ScanNet, which is very popular 3D indoor data set. The image is like 3 gigabyte, but a 3 scan is like 3 megabytes. So, of course, it will be perfect if the model can work without relying on 2D images. Right? Hopefully, the motivation is clear. Let's dive into the pipeline of OpenInstance 3D. So, given the 3D point cloud, the first thing we do is we use a mask module to generate some class organistic mask proposals. And then we have a snap modules, which will picking some good angles of the scene and capture a list of synthetic scene level images. And those images will be understood by a 2D open world detectors, and then we will store those results in a closed class lookup tables. And eventually, we will look through those class lookup table to assign a label to your proposed mask at the first stage. And it will yield the final open world instance segmentation result. We'll dive into each of the modules in next slides. Right, so let's talk about the mask modules. We designed a mask module based on Mask 3D. If you're not familiar with that, it's very similar to so the design concept of Mask 3D is very similar to segment anything models, which is released last year by Meta. So basically they use transformer decoder to convert your input token into masks. But what we did differently here is we're not only generating mask proposals, but also have a small mask scoring modules to kind of give give a score for each mask proposals to evaluate their qualities. And once you have those scoring modules, we will apply a thresholding of the mask scoring, and also we'll filter those low-quality masks with certain criteria. We're doing that, trying to get a high-quality, filtered class-organistic mask proposals. And the entire mask module is trained without using classification labels. Therefore, they're kind of they're fixed in the concept like class-organistic. So once you have those mask proposals, let's have a look at the snap modules. How can we actually take in images and then taking good images for scene understandings? Give us 3D point cloud. We position our camera above the scene evenly, and just to capture we're trying to capture the entire scene in the images from different angles. And then we not only do this at global level, but we also will dive into like each corners or using like wide angle snaps just to capture a list of images that can describe the scene quite well. The challenge of this part is once we position our cameras, we need to calibrate the intrinsic matrix to actually generate some good images. So we propose a very simple but effective module to calibrate this camera intrinsics. So once we have those images, we will also project the mask proposal we generate at the first stage with the same camera and intrinsics. So at the first stage, we'll also generate those mask proposals. And then once you project with the same camera pose and intrinsic, you will know exactly the precise pixel locations of each masks. And then that will be useful for future retrievals. Right? So you have your synthetic scene images. So what you do next is you fit them into 2D open world detection and segmentation models, just to understand what exists in this scene. And you have a detection results, which probably contains, there is a table, there is a couple of chairs, or there is a trash bin, or all those interesting objects that you will ask the system to search. It will just store them. It will just present in your 2D detection results. And then you also have your mask to pixel maps. We put everything together into something called like class lookup tables. But basically that is something we're trying to retrieve for assign label to the mask proposal in the first. Great. So for the lookup modules, once you have we have our 2D detection result, and we have the mask to pixel maps. So the way we do lookup is for every masks, you will actually see the overlap between your 2D detection result and the mask. Let's see for this one, the window here, you have a 78% saying that's window, and you probably have 6.7% see that was a counter. But overall, you just sample the result from different images, you will assign that to your final proposals. Right, and there's some cases where you won't get an assignment in this process. So to kind of force the model to give out outputs for those masks, we'll introduce some local enforcement lookup. Local enforcement lookup. Basically, it's like a small version of how this lookup module is done, but do it in locally. Right. So before we look into the result, let's have a look of some. I just want to have a high-level instruction on what's the benefits of this mask snap lookup design. So first of all, because we kind of completely outsource the 2D detection task to the 2D models, so we can actually switch different 2D models without trainings. So the performance of OpenX3D should be able to involve with the development of 2D models. And as we said, 2D is a way fast developing domain, so this will be a beneficial feature to have. The second thing is we can render less images compared to other models. We're talking about OpenX3D or other methods. They kind of like render images for each masks. But for us, it doesn't matter how many masks you have. We only render maybe 8 or 16 images, and that can also achieve quite good result. And lastly, we're talking about the impressive performance of Lisa, which can understand complex sentence and then do detections. If we change our backbone to that model, we can also achieve similar reasoning segmentation. Good. Let's have a quickly dive into the results. So we have achieved quite impressive result on several benchmarks. Some of them even has using 2D images. Yeah. So I just want to. So the first one we will have a look is the zero-shot classifications. Basically, I'm putting this result here because all this method here, they're doing a task that you only have 3D point cloud. I want to do a classification to see what they are. And you can see the list here. Uni 3D, which was a model just released recently. It was a pre-trained model, a large-scale pre-trained model. They call themselves foundation models and actually achieve quite impressive result compared to all the previous. But if we're using OpenEase 3D, use the snap and look up approach of OpenEase 3D, we can actually achieve like 50% higher than those well-trained, fine-tuned models. So this is why we believe the proposed snap and lookup approach is actually quite useful compared to others. Right, and also compared to other methods on open world 3D instance segmentations, we also show quite a lot of improvements, including the indoor dataset and outdoor dataset. And then if we convert the instance mask to objects, we can also achieve we also achieve a state-of-the-art result with a large margin compared to other object detection works. Great, but OpenEase 3D is by no means perfect. If you evaluate on some more challenging multi-label data set, for example, ScanNet 200, which has like 200 labels, you actually perform less well compared to OpenMask 3D. Yeah, this is because in that 200s, there's many of them are small classes, which in your 3D reconstruction, if the input is only the 3D reconstructions, they're not presenting very well in your point cloud. And OpenMask 3D, they can actually refer to the original 2D images. So yeah, that makes sense. And then for replica, which is a data set that is constructed quite well, if you can look at the images here. And we can actually achieve a better performance of OpenMask 3D. Right? So here's some of the demonstration here. If we use Lisa as the backbone, it can understand some quite abstract sentence like device to watch BBC News. It can highlight the TV here and furniture that is capable to produce music. This is, yeah, the piano is highlighted. And the third one, which is my favorite one, Malone's domain of excellence. Malone is a table tennis player, and then we got table tennis table highlights. Right, so I'm just going to show some quick demos of indoor scene understanding. As you can see, the mask proposal is doing relatively well, and then the instance, the classification, the classification task on each mask is also quite good. So that's the indoor. That's also indoor. Let's have a look at some outdoor data set. Like this is STBLS, which is quite sparse point cloud. But with this snap and local approach, we'll be able to understand like those building tracks and vegetations quite relatively well. Of course, there's some gap to fill in the future. Right. So last slide, I'm going to show the evolution of the snap photos. This is of course, we have explored quite a lot of approach until we reached eventually this scene level understandings. We even testing the method 6, which is exactly what OpenMask 3D has done, but we kind of give us this approach because that wasn't fit in our original task of using 3D only. Right. So a key observation here is once we switch from those object level of rendering to the scene level of rendering, the performance get boosted quite a lot. So this is one of the main takeaway of this work, that maybe scene level understanding will be a good approach for 3D open world understanding. Right, that will be all my talk. Hopefully it's not over. Well, so we have the project page, and the project is completely open source. Feel free to check it out on GitHub and maybe give us a star or something. But yeah, thank you very much.
Thanks, Zhening. Because of the limited time, maybe we didn't have questions. And we welcome our next speaker, Jian, from Canary University.